Systems and Chebyshev Polynomials. This corresponds to section 9.2 of the Cheney-Kincaid textbook. And last time you'll recall that we looked at the least squares method. We introduced that method and came up with an algorithm to solve this to produce a linear equation. We also saw that it was not just restricted to linear equations. In fact, one of the examples had us fit a table of values to y is equal to a times natural log of x plus b cosine x plus c times e raised to the x. We differentiated with respect to a, b, and c and came up with a set of normal equations. We then put these into a matrix and solved for the coefficients. So as a result, the non-polynomial least squares ended up looking pretty great. This one actually covers quite a few of the points, and it's best fit line. There is an outlier at 1 minus 1, but that's really about the extent of it. Everything else is very close. So the principle of least squares can be extended to general linear families of functions without involving any new ideas. So suppose that the data in the table are thought to conform to some relationship such as y is equal to a sum of some coefficients times a function or a set of functions g of x. These are the basis functions g0, g1 to gn, and they're known and they're held fixed. And then we determine the coefficients c0 to cn according to the principle of least square. So the question is what basis functions do we choose? And after we choose them, the least squares problem can be interpreted as follows. The set of all functions g that can be expressed as linear combinations of g0, g1 through gn is a vector space G. So what is the vector space that we want to actually go with? Well, one of these, in terms of what basis we choose, we want the system of normal equations to be easily solved or be capable of being accurately solved, if not easily. Let's give it a try with the first thing that comes to mind. And the first thing that comes to my mind are the polynomials. So consider a space G that consists of all the polynomials of degree less than n, which is an important example of the least squares theory. It may seem natural to use the polynomials of 1, which is x to the 0, x to the 1, x squared, all the way out to xn. And using this, we can write a typical element of the space G in the form c0 plus c1 times x plus c2 x squared, all the way out to c sub n times x raised to the n. This basis is pretty natural, but it's generally a poor choice for numerical work. A better choice for a basis are the Chebyshev polynomials. And this figure is an indication why the monomials or polynomials don't form a good basis for numerical work. The x squared, x cubed, x fourth, x to the fifth are all pretty close and pretty much alike. But the Chebyshev polynomials have a lot more range in terms of what they cover, and there's a lot more diversity there. So you can see the Chebyshev polynomials T1 through T5 cover a bit more range on the graph and are a bit more expressive in terms of how we can map a function. So how do we define the Chebyshev polynomials? So if you took 407, you'll kind of know the traditional notation is T0 is equal to 1, T1 is equal to x, T2 is 2x squared minus 1, T3 is 4x cubed minus 3x, T4 is 8x to the fourth minus 8x squared plus 1, and there's actually a recursive formula that you can use to put together these polynomials, and that gives a formal definition of the Chebyshev polynomials. So linear combinations of the Chebyshev polynomials are easy to evaluate because the special nested multiplication algorithm applies. In general, it's best to arrange the data so that all the points or the abscissas lie in the interval minus 1 to 1. If the original data don't satisfy that, then what you can do is you can do a change of variable to basically move the area in which they lie. And then you can apply the algorithm, which is on the next slide here, which is how you fit a curve with Chebyshev polynomials. Basically find the smallest interval AB that contains all the x sub k. Let A equal min x sub k and B is equal to max of x sub k. Then transform it to the interval minus 1, 1 by defining z sub k. Decide on the value of n to be used. Generally, 8 or 10 would be a pretty large value. And then using the Chebyshev polynomials as a basis, generate the n plus 1 by n plus 1 set of normal equations. And then using an equation solving routine, solve the normal equations for the coefficient in the functions. The text also has pseudocode that supports this procedure in case you're interested in writing it up. One of the important aspects of least squares procedure is smoothing of data. In this context, smoothing refers to the fitting of a smooth curve to a set of noisy values. And by noisy, we mean values that contain experimental errors. If one knows the type of function to which the data should conform, then the least squares procedure can be used to compute any unknown parameters in the function. However, if you want to smooth the data by fitting them with any convenient function, then polynomials of increasing degree can be used until a reasonable balance between good fit and smoothness is obtained. A good software library will contain code for the polynomial fitting of empirical data using the least squared procedure. Polynomial regression is a related idea. This was developed by Forsyth in 1957, and there's several pages of the text devoted to how this works. The math goes a bit beyond what we're attempting to do in this course. So basically just know that it uses a system of orthogonal polynomials that are tailor-made to the product at hand and uses the inner product of the polynomials. If the inner product is 0, then the set of functions are orthogonal. And an orthogonal set of polynomials can be generated recursively for this routine. There's a whole lot more in this section, but again, it goes beyond the scope of what can really be undertaken in a 1-month course. Anyway, thanks so much for watching.